Right, so we continue with how photons and metal interact, and in fact we are talking about 4.2.3, right, how the energy is of concern to us. Okay, so to reiterate, the photon transfers its energy over to the electron and metal. Conservation of energy is maintained in this equation. Right, so this is a general equation because we have mentioned earlier, right, that electrons at various depths of the metal requires different amount of energies to eject. We have a range of energies here, and hence there must be a range of energies here. Okay, that's what we know. So to put that into an illustration, if a photon coming of the same energy, if it interacts with electron on the surface, it goes out, right, with a high velocity. If one that's interacting with an electron that's deeper within the metal, the electron comes out with a much lower velocity. Okay, simply because of this conservation of energy equation. So when I introduce the work function, I haven't related that to the threshold frequency. Now I can talk about them together. Right? If I slowly reduce the frequency of the light, I will be slowly reducing the energy of the photon. There will at one point, there's one minimum frequency where electrons are ejected with 0 keV. Even the surface electrons are ejected with 0 keV. So energy of the photons is given purely to the metal, right? And we know that the energy given electron is 0. So this means that the work function of the metal must be equal to that minimum frequency. And here we define work function and threshold frequency together. Okay, we equate them together. We can say that the work function must be equal to Planck's constant multiplied by the threshold frequency. Okay. And so for every metal, there is a threshold frequency. So if you look at the page 6, right, I give you the work function of various metals. You can actually go and calculate, just for exercise, what are the threshold frequencies for each of the metals. Okay, you will find that for reactive metals like sodium, visible light is enough to eject electrons, whereas for metals that are more stable, you will need ultraviolet light. Okay. Right, example 4. For the metal sodium, calculate A, the threshold frequency, and B, the maximum speed at which electrons will be ejected if wavelength of 405 is shown on the surface. Right, let's try. Threshold frequency. Right, the energy of the photon must then become the work function. The energy of the electron is 0. Okay? So E equals HF naught equals to 5. You rearrange, you get the threshold frequency of the metal. Okay? We're going to find, however, the threshold wavelength also. So we recalculate, we find that this threshold wavelength is this value. Right? This value falls squarely in red color. Right? It's about 650 nanometers. Right? So as long as your wavelength is shorter than 651 nanometers, thereabout, electrons should be ejected. Okay? So here I want to show this idea. For frequency, there's a minimum. So the higher the frequency, the more likely for electrons to be ejected. For wavelength, it is the shorter the wavelength that allows for electrons to be emitted. Right? So if red color ejects, blue color, yellow color, green color will definitely eject. Infrared will not. Okay? Right, next. Part B. We want to find the speed at which electrons will be ejected. So actually, Einstein's equation, you don't really know yet, but essentially this is the energy of the photon. On this side is the work function of the metal. And the rest is the energy of electron, which we take to be half mv squared. So even without introducing to you Einstein's equation, I can already do this formula. And in fact, I've been building you up to know Einstein's equation that when you look at it, it actually feels very intuitive. Right? So energy of incoming photon, whatever is given to the metal, the remaining must go towards the electron. So if you know everything else of the energy coming in, the energy being given to the metal, the rest must be the energy of the electron. So you rearrange, you can find the speed of the electrons to be 6.4 10 to the power 5. So example 4 is actually a bridging kind of a question because later on you will see how it all works again. Right. Any questions at this point? Okay, conservation of energy. So lastly, we can talk about the photoelectron part. Right, remember at the very start of the lecture 1, I said that for the electroscope, the one with the gold leaf, observation 1, 2, and 4 can be easily seen. But the one about the kinetic energy of the electrons, right? I said you cannot really see an electron. So how do you know what is its maximum energy? So there must be a smarter way to measure the energy of electron in a macroscopic way that humans can see. Right? So this, we need to revisit what we have learned in electric fields. Okay? This H9, right, in your lecture notes is new. I included it because throughout the time I've lectured, okay, by right, this is in your electric fields. By right, you should know. Throughout my own experience of lecturing it, students generally are lost. So I want to reiterate this key point. Okay? So I use an example to illustrate this point. Okay? You have a plate that is positive here, and you have a plate that is negative here, or rather 0. So the electron actually experiences a force to the left. Do you agree? And between the plates, the field is constant. That means the force is constant. So the electron constantly feels a force to the left, much like my pencil case will constantly feel a force downwards, which is uniform and constant. Right? So if I am giving the electron a certain Ke to the right, it is like me giving my pencil case a certain Ke outwards. The electron will travel outwards as my pencil case traveling outwards. It will reach a certain height, the speed will turn 0 and turn back down. Correct? Yeah, it's the same idea. It's a conversion of energy from a Ke to a potential energy. Okay? When you throw a pencil case out, it's a conversion of Ke to gravitational potential energy. And in the plates, it is a conversion of Ke to electrical potential energy. Right? So, let's recap. What is the electrical potential energy gained by electron as it moves from plate A to B? All the answers jump out. So let's look at the first one first. Maybe I can do some. I can't. Yeah, the Microsoft changed the version, so there are some things I can't do anymore. So the first one, the change in potential energy, right? It's the charge times the change in potential. Right, this is what you have learned in electric fields. You should know it. Here, we learned that the charge is negative. The final potential is 0. Initial is plus 5. So it's 0 minus plus 5. So you get 8. Right? So the potential energy goes higher as you go towards the right side of the plate. Okay? Express this answer in EV. Right? So you see that if you want to express 8.0 10 it's so difficult. Whereas 5 EV, you see the beauty, it is exactly the potential difference of the plate. Okay? Part C, if electron A leaves the plate A with kinetic energy of 6.0, does it reach plate B? And the answer is yes. Right, because 5 eV of energy is converted from KE to electrical potential energy, leaving you 1 eV of KE. That is to say, if I need 6 joules of energy to throw my pencil case from this table to the ceiling, if I gain 5 joules of energy from this table to the ceiling, and I throw this pencil case with 6 joules of KE, I will reach the ceiling. Do you agree? Right? Nod your head if you agree. Raise your hand if you are unclear. I need you to be with me on this bandwagon. Alright, no hands means yes. So, D, if I then throw the electron with an energy of 4, can it reach plate B? Answer is no. Right? Actually, answer is just no, it does not. The rest is just to illustrate. So if I throw my pencil case up with energy of 4, and I need 5 to reach the ceiling, can it reach the ceiling? No, it's the same idea. Why is this important for quantum physics? Because we want to measure the energy, the maximum energy of photoelectrons. Right? And if we are able to, why did it hang? Okay? And this allows us to measure the kinetic energy of the electron through the potential difference. Why? Because I can attach, right, for plate B, I can attach an ammeter on this side. Every time electron hits it, the ammeter will register a current. So I attach ammeter connected back to plate A. Right? Every time electron hits plate B, I will register a current. So what I can do is then slowly increase the potential difference until I measure no current. Right? That's like me. I have I can throw this pencil case out with a range of energies 1 to 10. And I slowly increase the gravitational field until I cannot reach the ceiling. And then, okay, now I cannot reach, I know what is the energy of the pencil case. Okay, one more time. Let me try the energy again. Let's say I can throw the pencil case with a range of energies that I don't know of, unknown. But I know how much energy, but I can change the gravitational potential energy required. And through that, I can measure the KE of this pencil case, which is the energy for the electrons. Okay? So this is what this very powerful equation is trying to say. This equation shows how to measure the microscopic through the macroscopic. Right? I can measure the speed of electron through the potential difference of the plate. Amazing. Okay? Right, so this is quite a nice idea that the scientists have. Okay? Okay? And this is a key page that you must come back to understand Einstein's photoelectric effect equation properly. Any questions at this point? Perfectly fine. Clear. Okay. So then we can talk about how else to measure the rate of arrival of photoelectrons. Right? If you cannot see the speed, you can use the potential difference to calculate the kinetic energy. But how do you count the number of photoelectrons? How do you count the number of photoelectrons? We use ammeter, right? If we make plate B positively charged compared to plate A, all the electrons that are emitted will be attracted towards plate B, all of them. Then this allows to calculate all of the electrons being emitted. Okay? Very, I'm showing these concepts to you in a slow way, right, so that later when I give you the big piece, everything falls on place. Okay? So you must promise to come along with the ride. Huh? So, once we know the current, if plate B I attach an ammeter, I know the current, I know the charge because they must all be electrons, I can find the number of electrons over time. Note that this is the rate of emission of photoelectrons, not photons. This is electrons. Okay? At this point, if you still are not clear about what is a photon and what is an electron, you should try to. What is a photon? Photon belongs to electron. Is the one that comes out from the metal, okay? There are different things. Because I have seen, okay, I know this is not going to happen to many of you, but I have seen students confuse electrons with photons, and they wrote E equals to HF for the electron. Okay? And that is just wrong. Okay? So please divide the two in your mind that have a space for each other. Right. Then, right here I also recap and contrast to you the difference between photons and electrons. Right. So first, the one on top is electrons, the one below is photons. Not the same thing. Right. So I recap what I've done in lecture 1. Okay, and page 10, the last paragraph, I'm going to demonstrate to you. Right, so this is the observation number 4, right? That the intensity is proportional to the rate of emission of electrons. So if you have 2 light coming in, let's say 1 electron comes out. If you have 4 photons coming in, you have proportionally 2 electrons coming out. Okay, that's basically what it means. Can? Okay, if intensity is doubled and frequency is kept the same, the number of electrons is doubled. Right, so finally, oh wait, before you can move on, let's try. Photons are emitted when light is shone on the surface. What happens to the maximum K of electrons when frequency is increased? Right, using the conservation of energy equation, how does that work? Okay, part A. Take 30 seconds, think of your answer. Okay, now can you share it to your friend, to your left and right? Okay, part A. Frequency is increased. What happens to the speed of electrons or maximum K of electrons? What is the answer? It is increase or decrease? It is yes, it is. So much energy, man. Woo. One more time. If the frequency of the photon is increased, what happens to the energy of the electrons with high energy? 1, 2, 3. Wow, so high. Woo. Okay, it is increased. Well done. Right. Part B. What happens to the maximum K of electrons when the work function is increased? How do you increase the work function of a metal? You change the metal, right? That's one way. We replace sodium with platinum, for example. 30 seconds, discuss with your friends left and right. See if you all get the same answer. Okay, so if the energy of the photon stays the same, the work function is increased. What happens to the energy of electrons is 1, 2, 3. Decrease, right? Thank you. Because I only hear increase. Alright. Right, okay, finally we can jump into the real meat of the photoelectric experiment. I've done all the setup, right? The whole lectures until now is a setup for this one experiment. It's to lay the ground. And there are a few guiding questions that you must be able to answer. How do I draw the setup? I have found the simplest setup already. This is as simple as it gets. Okay? Number 2, why do you need vacuum within the setup? And number 3, is it just a conservation of energy equation? It is not, right? So what is the difference? So let's start. Photoelectric experiment, you have incident light hitting on the emitter, and electrons are emitted out towards the collector. These electrons will then travel and register on the microammeter, travel through this circuit, and come back to the emitter. You have an adjustable PD here. This is the cheat, right? In previous years, I drew the setup of how to make this adjustable PD. Okay, but that is confusing because it requires knowledge of DC circuits, which by right you should know, but I'm trying to simplify everything just down to quantum. Okay, so as you adjust this PD, this potential difference, this voltmeter here, will measure that potential difference. Okay, so remember just now we were trying to measure the number of electrons through the emitter. We're trying to measure the maximum Ke of the electrons through the voltmeter with a stopping potential. Right, so this is the true setup for the photoelectric experiment. Right, that's all I've said. Right, the rest that just appeared is what I've said. Why is it performed in a vacuum? It's because if you have electrons coming out and they have air in between, do you think the electron can reach the collector? Answer is no, right? Because the electrons will be absorbed by the air, and you will not be able to very sensitively measure the amount of electrons nor the Ke electrons, because you will hit the air particles, you reduce and lose its Ke. Right, so I'm answering one of the questions for you of why you require a vacuum. Okay. So this is the setup. Number one, the guiding question number one. Number two, why you need a vacuum? Okay, both are there. Right. Finally, I can talk about Einstein's photoelectric effect. At the start, I gave you the equation of energy of photon is energy of matter is energy of electron. How does that differ with this exact equation, this equation? What's the difference? The difference is this. Einstein's photoelectric effect measures the work function of the metal, not the energy of the metal. What does that mean? It requires the minimum energy to the metal, which means the energy of the electron emitted is the maximum. Right? That means Einstein is looking at a very particular condition. Right? You have many photons coming in, you have a range of electrons coming out, a range of energies, but you're looking at just the fastest in Einstein's photoelectric experiment. Right? So energy of photon does not change. Work function, he chooses the particular energy, the minimum energy required, which means whatever you have left is the maximum energy of the electron. Okay, so this is Einstein's photoelectric effect. And naturally, if you are pretty strong, right, you can see that HF can become HC over lambda. Work function can become HF naught, where F naught is the threshold frequency, and half m EV max squared can become stopping potential EV. So every component of this equation is replaceable by an alternative. Right, so although this is Einstein's photoelectric effect equation, there are multiple versions of this that says the same thing. Okay, so energy of photon, one more time. If you didn't hear me, I say again, I say slowly. This can be replaced by Hc over lambda. The work function of the metal, if they didn't give you the work function of the metal, they can give you Hf naught. Right, the threshold frequency of the light plus H times H, or they can give you Hc over lambda naught for work function. So actually there are three things here. For the maximum K of the electron, either they give you half m V max squared, or they can give you the charge of electron E multiplied by Vs, a stopping potential that you measured, that you measure. Okay. Right. So now let's get a good understanding of what's happening over here. Right, through the IV graphs. It's like, hey, isn't there one more lecture? Yes, there is. But this is so much information in a few graphs that we can take a lot of time just to explain these graphs. How is the IV graph obtained? Right, that is the guiding question. So this is the same setup except for a few changes. Note that now I include, instead of adjustable PD, I show you how the PD is adjusted. Okay, so if I have positive potential here, this collector is positive potential. If I have negative potential here, the emitter is negative potential. So what does this mean? Every electron that comes out, it will want to move to the, you experience a force to the right. So every electron that comes out will be collected. Okay, that is the first change of this adjustable PD. Second, there's a quartz window here. Why a quartz window is because it can, why not glass? It's because glass absorbs UV light. Right, so quartz window allows all from visible to UV light to pass through. Right, so what's happening here? There's a whole chunk of words there, and I'm trying to explain it to you with my diagrams. So you have light coming in. In red, nothing happens. In purple, UV light, electrons comes out, and a current is created. Okay, and this current is constant. Here is another example, right? I now flip the right-hand side of this. into a horizontal melee, and I'm going to show you. If I connect to this point, it moved. Sorry, if I don't connect, there's no potential here. It's a neutral. All the electrons, the slow one will reach, the middle speed one will reach, the fast one will also reach. Agree? Right, so you have here at zero potential difference, a fixed current, right? A current of made of 3 units worth of electrons. Now watch what happens if I place my jockey down. What happens? C becomes plus, E becomes negative. So what happens? They all feel a charge to the right, a force to the right. So every charge that's emitted reaches the collector plate. So what happens? You increase the V a little bit, you don't change the I because every electron that has already been emitted has been collected. If I increase the V to maximum value, same thing happens. Every electron that comes out must be collected. So you have this. You essentially draw a straight line to the right. Okay? I've now explained the plus V side of the graph. Let me now talk about the negative V side of the graph. That's the interesting one. So watch what happens. Watch the screen and sorry, magic is not happening yet. Ready? No, not yet. Damn. Here, watch. Ready, go. Ding. I have flipped the battery around. Now what happens? The emitter side is positive. Alright? So watch. I flip it around. The emitter side is now positive. So what happens now? Now the electrons actually experience a force to the left. Will every electron reach the collector? No. The middle speed one will lose velocity as it goes to the right. The fast one will also lose velocity as it goes to the right. But the slow one, it will. Okay? Which means the total current you measure must be less than before. Okay, is everyone with me on this point? If you are not sure, please raise your hand. Okay, I give you 30 seconds, discuss with your friends. I see you discussing, so I think there should be quite a number of you who are not sure. Please discuss with your friends to clarify this question, this point. Okay, very good. Right, a lot of fruitful discussion, and I hear a few questions. Right. So what happens now if I increase the potential difference? Watch, I move the wire now here. What happens? It's even more positive on the E side and even more negative on the C side. That means the potential difference has become more and more negative. What happens? The slow speed one can reach now. Already cannot reach, so now even more cannot reach. Right? Come out. See? Even less distance. Can see not? Compared to before. Right? The distance it came out is less. The middle speed one tries very hard and doesn't reach. Cannot reach. So about the fast speed one, touch. Oh, hey, still can touch. So there's still some current there. Current is not reduced due to the larger potential difference. Okay? And so if we continue to increase the stopping potential, to increase the potential until the point where all electrons, of course, cannot reach now, right? And the fastest one is, cannot reach. Now we got zero current. What is this? This potential that we measure across the circuit is, what is it called? It's called it stopped all the electrons, and it's a potential. What is it called? It's called the stopping potential. Okay, can? So this is how the setup is used to measure the stopping potential, which is a proxy to the maximum Ke of the electrons. Done. Right. We got some time, so let's talk a little bit about the other graphs. So the rest of this chapter is about how you can manipulate various factors and change the graphs. And not just IV graphs, but some other graphs that are also important. Okay? So if you understand the photoelectric effect and you understand the equation, all of these graphs can be created by you. Okay? And one of the key questions that always come up is, when intensity or frequency of all of the metal is changed, how do the IV and VF graphs change? Right, there are two main categories of graphs. IV, which is what I showed you just now, but there's also a new one called VF graph, potential difference versus frequency graphs, or rather stopping potential versus frequency graphs. So we call this right. So the equation here, right, like I said just now on page 11, right, your equation can become this. Your stopping potential appears, manifests itself in the measurement of the kinetic energy of the electron. So if you have of photons of different frequencies, you will change the stopping potential. If your F is higher, the stopping potential must be higher. Agree? So here, frequency 3 is larger than frequency 2, is larger than frequency 1. So the stopping potential 3 must be larger than stopping potential 2, must be larger than stopping potential 1. Okay? That is essentially the graph you have at the top. Okay? That means we redid what I did with you. We redo what I've shown you by slowly increasing the stopping potential for 3 different photon conditions. Okay, and I arrived at 3 different stopping potentials. Now, it is also very interesting to look at this at the stopping potential versus F graph. I want to introduce to you a new graph, which is the stopping potential versus F graph. And to do that, I will take this equation, I will rearrange with stopping potential to the left-hand side, and I get this equation. So you see that your stopping potential, note that stopping potential is not your V at any V, it's a fixed V, one fixed V. It's your y-axis, your frequency is the x-axis, and the gradient is h over E. Work function over electron is the y-intercept. What do you get? You get this equation. And you can plot it like this, because y, you know Planck's constant, you know the charge of electron, you can plot it like this. Right, Vs is your y-axis, F is your x. The gradient is h over E. The y-intercept is negative 5 over E, which you can dot, and you get negative 5 over E. Okay? Can you dot it in, because it's not in your notes? Right, and how does this graph relate to the previous diagram? Oh wait, here I must explain to you where this graph cuts the x-axis, that is the threshold frequency. Naturally, right, that's because when your y is equals to 0, right, your phi is hf naught. I need to show you how it relates to each other. Right, so for the same metal, listen carefully, for the same metal, I changed the frequency just now. So I used frequency 1, I had stopping potential 1. I changed the frequency 2, I found stopping potential 2, so I mark it here. And I did stopping potential 3, for frequency 3, I mark it here. So on your V versus F graph, I can draw this line by connecting the 3 crosses and extend it to this point to find the threshold frequency of the metal. Okay? So that's how we find the threshold frequency of the metal experimentally. Can? Just one other way. Right. So this is how we view stopping potential versus frequency graph. Any questions? Right. So if there are no questions, then I can introduce the next graph to you. Is when we change the metal, what happens? Remember that the intersect at the x-axis is the threshold frequency. If we change the metal, having different work functions, we will have different threshold frequencies. The higher the threshold frequency, the more stable the metal. So cesium is very reactive. It will have a very low threshold frequency. Potassium, reactive also, but less so. The threshold frequency will be higher. Beryllium, higher. Notice that the gradient stays the same because you are not able to change H over E. You can also extend the y-axis and find the y-intercepts, and you can see how the work function changes. Okay? Right, we'll stop here for today. Right, thank you for your kind attention. We'll continue with page 14. Next lesson, 14, 15, 16. Okay, so we have 3 more pages to go, and we can call quantum 1 the end. Okay, thank you very much. If questions, come forward. If not, this is the end. Bye-bye.